Today, I'm looking forward to talking with you about some of our work at WCC. We've been working on this project for about 3 years now, and we're getting closer to the finish. So we're starting to get some interesting insights into things. I appreciate your feedback and questions, so feel free to ask as we go along, and particularly follow up in the question and answer session or after the presentation. And I'll just go ahead and get started. So the big question that we're trying to answer is, how much money should you invest in efficiency upgrades or solar power when you're building a new commercial building? And you really have to balance the value of the energy savings versus the costs of those investments. And how you balance that and what you pay attention to really depends who you are, what seat you sit in. So when we started thinking about this, we came at it pretty simply, and we've been peeling back more and more layers over time, and still just growing in our understanding of the whole market for new building design, construction, rental, maintenance, the whole ball of wax. So different stakeholders have different motivations. The first stakeholder I start thinking about is the developer, the group of people who are building the building. Often this is a group of people that are building the building as an investment and then plan to sell it. They plan to sell it to someone who's going to become the owner. And then typically the owner leases or rents the building to the building occupants. The utilities provide energy and water and other services to the building, and then the building interacts with society at large. So each of these stakeholder groups have different perspectives. The developer is typically trying to build the building for the lowest cost that still meets code requirements, and is also trying to build a nice enough building to attract good tenants and retain good tenants. A building owner who's bought the building after it was built really wants a reliable, low maintenance, and attractive building. The building occupants typically, in the majority of cases, pay the utility costs. And so they're the ones that would be interested in efficiency, but typically most of the efficiency investment decisions have been made and implemented long before they come on the scene. The utilities are tasked with providing the energy services to the building, or providing energy, electricity, and natural gas to the building. And they often have an interest in reducing the total amount of infrastructure that they'll have to build. And so they're interested in decreasing the peak loads from the building, and particularly in California now with the famous duck curve, interested in reducing the ramp rate and the loads on the grid in the evening when solar production starts to go down. And then finally, society at large is really interested in reducing the emissions, reducing the health costs and climate change costs from emissions, which the majority of the emissions from the building will be due to its energy use typically. So in the past, in particular, the developer interest in low cost has meant that the lowest cost equipment and design options were chosen, even though those were often low efficiency, high energy consumption options. And that was in direct conflict with then the occupants wanting to reduce utility costs. And this conflict, the landlord-tenant problem or principal agent market failure problem, exists in most of our commercial buildings, and has really prevented an economically efficient level of energy efficiency investments from happening. This has started to shift a little bit as new code requirements have raised the bar and increased the efficiency level, or even required zero net energy building designs, and now are starting to require photovoltaic systems to be used. these new requirements are starting to reduce that conflict because they're requiring the developer, in order to meet code requirements, to already build a pretty efficient building that has lower utility costs. So this is starting to bring these into less and less conflict, and that's really interesting. So in this project, we were trying to answer the question of how do you get to a lowest cost design? We're interested in the construction cost. We're interested in the operating costs, energy and maintenance. We're interested in the cost to society, including kind of the need for utility infrastructure and also the emissions from the building. And there's a couple ways to approach that part of the question. One is called time-dependent valuation, and another one is marginal greenhouse gas emissions. And in this presentation, I'm going to focus mostly on construction cost versus this bigger picture cost that's defined by time-dependent valuation. So time-dependent valuation, I'm not sure how many of you are already familiar, but I'll just say a little bit about it. Happy to talk about it more and can point you to some references and resources if you want to dig into it. Time-dependent valuation was a metric developed by E3 for the California Energy Commission to be used particularly for building energy efficiency code compliance purposes. It is an attempt to get into one metric the cost to society of a kilowatt hour of electrical energy used, or a therm of natural gas energy used for every hour throughout the year in each California climate zone. So each of the 16 California climate zones have their own 8,760 hourly values for the kind of cost of society for using energy at that time in that climate zone. And this is an example here of the average of those hourly values across the whole year for California Climate Zone 12, which is where Davis and Sacramento are. So you can see this includes the retail markup for the energy, the wholesale cost of the energy is the, moving up from the bottom, is the next navy bar. We've got the losses in the grid, ancillary services supporting the grid, the cost of emissions in terms of health and greenhouse gas climate change emissions impacts, the costs of the renewable portfolio standard, of getting to larger and larger levels of renewables on the grid. And then you see the ones that really change a lot with time are the capacity, the cost of having standby power plants ready to produce more energy in case the predictions about how much energy the whole grid is going to need at every moment aren't exactly right. And then the cost of the transmission and distribution. And that cost is really driven by the peak usage of energy. You have to build the wires and the infrastructure large enough to deliver enough power for the peak loads. So this is the annual average, and you see that it's about 2 times the late afternoon, early evening time period. The value of energy is about 2 times the average value. But then if you switch to looking at the hourly values themselves instead of the average over the year, you can see that then the peak hours are as high as 29 times the average value for the rest of the year. So this means that when you're thinking about the societal value of energy, the time that your solar panels produce energy, the times that your efficiency measures save energy really matter. That just adding up the total amount of energy over a month or over a year doesn't really get you enough information to evaluate what the best options really are. And so things that save or generate energy during these peak times will be more valuable than ones that save energy during the average times. So to compare solar panels, photovoltaics, to different types of efficiency investments, efficiency upgrades, efficiency measures that could be implemented in the new building construction, we've started looking at this metric where we calculated the total TDV value saved per dollar spent on each of the possible investments. And we've looked at solar systems, we're starting to look at batteries, we've looked at over 50 other energy efficiency measures, and starting with a baseline of Title 24, 2016 code compliance. So the buildings start out pretty efficient for our baseline, and then we're looking at what's the cost optimum way to get from that pretty high bar as far as we can towards Z&E, and what wins. Is solar more cost effective, or are the energy efficiency measures more cost effective, and which ones of them are the most cost effective for different types of buildings in the different climate zones. So we started out with, we have 11 different commercial building types that we're looking at. Here are 4 of them, just renderings from the Energy Plus models. We started with the US Department of Energy prototype energy models, and have made adjustments to them to bring them up to code and get them to work better. We do simulations of those baselines and look at how much energy they consume and how much would cost to build that baseline building. And then we look at options for upgrades. Like here's a picture with the strip mall building here with photovoltaics on the roof and skylights. And we look at the energy savings from these 50 different efficiency measures and from solar panels. And we look at the cost of construction. So overall, we look at how much it costs to increase the efficiency and what this does to the upfront cost of the building. So to start out, our bar that we're going to compare all other efficiency options to is really the cost of the solar panel systems, the cost of the photovoltaics. And so we've done some work looking at the cost trends and reached out to a couple different groups to get up-to-date cost information for not just the panel costs, but also the racking, the wiring, the inverters, the labor, everything that goes into it. And these costs have been coming down steadily, and the average efficiency has been increasing. So overall, the cost per watt of DC rated power has been going down over time. So relatively up-to-date costs for including the overhead and profit for the suppliers and the contractors that are installing the system during the new building construction. We see that roof-mounted systems can cost about $3, a little over $3 per watt, and a little under $3 per watt if they're larger systems, so over 100 kilowatt systems, which for many commercial building types, they need more than 100 kilowatt systems. So most of the buildings would use that on their roof. And then also for most of the buildings we looked at, they can't fit enough solar panels on the roof to zero out their total TDV value for the year. And so they would also need additional solar mounted on canopies over the parking spaces. And this costs almost twice as much as the roof mounted ones, because you have to pay for that whole structure that's holding those solar panels over the parking spaces. So doing solar production modeling, the power production modeling for the solar systems in each California climate zone, we come up with an And using those cost numbers, we come up with a TDV saved per dollar spent on the photovoltaics. And then we have this arranged so that we've got each of our 11 building types across the x-axis. And then, for instance, the high-rise apartment building, then we have the PV modeling across the 16 California climate zones. And so we see per dollar that we'd spend on solar power, how much TDV can be saved. And you see that the sunnier climate zones, you save more per dollar, and the cloudier ones, you save less. And then you notice this distinct jump here. These 4 building types to the right could fit all of the solar panels they needed onto their roof. So they could use the lower cost solar panels instead of having to pay for the canopy panels. And so you could see that they're almost double the TDV saved per dollar for solar panels. So now we want to compare other options for reducing the energy consumption of the building, evaluated with that TDV metric to this photovoltaic TDV saved per dollar. So one of the first ones we investigated was looking at adding insulation. That there's a few different ways to add insulation to these types of buildings, and the costs, including materials, labor, overhead, and profit for adding wall fiberglass bats was about 12 cents per nominal R value per square foot of wall. With rigid foam board, it's about 30 cents per nominal R value per square foot. And then for closed cell spray foam, it's 33 cents. And we did a series of modeling steps where we looked at the 11 building types across the 16 climate zones and 5 different steps in terms of the additional R value for the insulation. So 880 annual simulations, looking at walls, roofs, and then the slabs or basement walls included to see what the TDV saved per dollar spent on insulation would be. So here are the results. Again, we have our 11 building types, and we have for each building type, in each climate zone, we run through the 5 steps of the insulation thickness that would be added, or the extra R value that would be added. And what stands out to me is that you see that for 2 of the building types, adding additional foam board insulation to the exterior walls actually gives you a negative TDV savings. And these particular buildings have pretty significant internal heat loads in the large office from IT closets that are generating a fair amount of heat for computing, and in the large hotel from the laundry and the commercial kitchen interior there. And so that if you add insulation in some climate zones, you're just making it more difficult for that extra heat to get out of the building. So you're actually hurting yourself by adding more insulation. In most climate zones, it is a benefit to add the insulation. You get some TDV saved per dollar. And now if we compare that to the solar systems, what you see is that for almost all the buildings in almost all the climate zones, it's more cost effective to put on solar, to invest $1 in solar than it is to invest in extra insulation. And there's a few cases here for the big box retail store, standalone retail store, 1 climate zone for the large office, and 2 climate zones for the large hotel, where excuse me, where it would be more cost effective to spend those dollars on insulation and reduce the size of the solar system that you would need. So this was interesting to us. This was surprising to me. I expected a lot more of the buildings to make sense. And two takeaways here. We found that the foam board insulation, even though it was more expensive per nominal R value of material, since it's put on the exterior of the building, there's no or very, very little thermal bridging. And so it's actually less expensive per effective R value than adding more insulation interior to the walls, where the studs or other structural elements reduce the effectiveness due to thermal bridging. So moving to another option, is it better to spend your money increasing the efficiency of your HVAC systems, or is it better to spend your money buying more solar power? So most commercial buildings use packaged HVAC systems like this rooftop package unit in the picture here. These types of package systems serve about 90% of the total commercial building area in the US, and about 80% of the packaged rooftop units sold are the models that have the minimum legal efficiency level, the minimum efficiency level that's allowed to be sold by the efficiency standards. So looking at the cost to upgrade from this minimum legal efficiency to higher efficiency systems, we found a range of costs that was a pretty wide range, and it depended on the starting level of efficiency. It depended on some of the features of the devices. And our first cut analysis is to look at the high end of this range to say, can we afford even the high cost upgrades? So, and this is the dollars to increase the COP of a unit by 1. So to go, say, from a COP of 3 to a COP of 4, and then per ton capacity. So the larger the unit and the more you want to increase the efficiency, the more it will cost. Again, we did the modeling with 11 building types, 16 climate zones. We looked at 9 steps in COP for almost 1,600 annual simulation runs. And we see our results here that look really different from the insulation results. In this case, almost all the buildings and almost all the climate zones, it makes sense to increase the COP of the HVAC systems, even when we use the highest cost of the range that we found. So this means that for most buildings in most climate zones, it's going to make sense to buy higher efficiency equipment than the legally minimum required, even though that's not what people actually do. A few cases where that's not true, the warehouse uses very little heating and cooling energy, since it doesn't heat or cool the space very much at all. And in a couple of the mild climate zones, in a couple of the building types, it also made more sense to put your money into solar than into higher efficiency HVAC equipment. But for most of the buildings in most of the climate zones, it makes sense to upgrade your HVAC systems. So our future work, we're continuing to run our full matrix of modeling runs, over 1 million annual simulations. We're looking at over 50 efficiency measures. These results that I showed you were individual efficiency measures, holding everything else constant, but our million model runs will include interactions between the different efficiency measures. We're working on the battery electrical energy storage options now, which look like a promising way to reduce TDV in a cost-effective way. And we're extending our analysis to also include the utility costs using the real retail rate tariffs. And we have a stretch goal to also include some marginal greenhouse gas analysis to see if those 2 other ways of rating the optimum design line up with the construction cost versus TDV analysis. And I'll end there, and thank you very much for your attention.
Thanks so much, Dave. Really interesting. So let us know if you have some questions for Dave. Just enter your name in the chat box, and I'll go ahead and unmute you so you can ask your question. While we wait, Dave, is there any plans to do any residential type analysis? Because this is on new commercial, right?
This was on new commercial buildings. It includes apartment buildings, so there is that section
Yeah.
residential.
Yep.
We haven't tackled the single family home area there, mainly just because we have a lot more expertise in the commercial buildings and the models and modeling of them. But we're interested in partnering with folks who are experts in those areas to try to extend this type of work.
Okay. All right. Well, we'll pass the presentation over to Claire. If you do have questions, you want to follow up with Dave, I'm going to put his email here in the chat box, so you can follow up with him. And he'll also stick around, so if you have questions at the end, feel free to ask him then. I will go ahead and let's see, Claire, we're going to pass the screen to you.
Okay, so hi everyone. I'm Claire Sugihara, and I am a second year student in the Energy Graduate Group. And so today I'm going to be talking about some research that I've conducted over the past year on fleet electrification at the Plug-in Hybrid and Electric Vehicle Research Center at UC Davis. And so one thing I wanted to point out is that electric vehicles can mean a few different things depending on context, but for this project, we're looking at plug-in electric vehicles, which includes plug-in hybrids and full battery electric vehicles. Okay, so a little bit of background on why we're looking at fleet vehicles as opposed to personally owned vehicles. So first of all, we are looking at how fleet managers make purchase decisions for a large number of vehicles. So convincing them about the importance of electrification can make a larger impact than convincing just one private consumer about electrification. Also, by driving and interacting with the fleet vehicles, users have an increased awareness of electric vehicles and are more likely to purchase one for their own personal use. Also, these vehicles have a higher than average annual mileage and turnover rates, so electrification can have a greater potential to reduce emissions. From a more traditional energy perspective, fleets have an increased impact on the grid because of the large number of vehicles that they purchase. So understanding their charging behavior is really important. So these interviews were conducted over a 7-month period, concluding in September 2019, and were done in several areas around the state. They covered over 86,500 vehicles and pieces of equipment, and the majority were done with city and county fleets, including police departments and utilities. And so we did not sample any private fleets in this study, but this could be a good area for future research. And we had a pretty large variation in the size of fleets, including small fleets of around 250 vehicles, and our largest fleet was around 12,000 vehicles and pieces of equipment. So we began by asking fleets a variety of topics, such as how they make their vehicle purchase decisions and if the organizations have any sustainability goals and their perceptions about their purchase intentions for used EVs. We then asked them about their thoughts and experiences with used vehicles and used electric vehicles. So looking at how they purchase vehicles, we began by asking the fleets how they choose what vehicles to purchase for their fleet, and we found that compatibility of use was the most commonly mentioned purchase consideration. So talking more about compatibility of use, this means looking at whether the vehicle meets the requirements of the job that it needs to perform. And these specifications are generally developed by the fleet team and then sent to the dealerships for bidding. And then the managers choose the vehicles that most closely fit these specifications. And while this may seem pretty simple, like the fleet vehicle needs to meet its intended purpose, we did hear many stories about vehicles that had been purchased only to find out after the fact that they were not going to be able to perform their necessary functions when they were given to the end user. So then looking at purchase price, if multiple vehicles met all of the bid requirements, then fleets generally chose the vehicles with the lowest upfront cost, which is generally mandated by the organization's leadership. Under certain situations, the fleet managers were able to purchase a vehicle with a slightly higher bid price if the vehicle had issues such as having historically higher maintenance costs, or if they were seeking to standardize on vehicles from a certain manufacturer. So maintenance cost was the third most mentioned purchase consideration. And despite the fact that all the interviewed fleets had their own maintenance facilities on site, the maintenance costs were still a highly ranked purchase decision for 12 fleets, which may be because fleets reported being understaffed, and so they still needed to rely on outside support from the dealerships, and they were trying to minimize this. So then moving on to total cost of ownership, we found that purchase costs were ranked highly as a purchase consideration, but total cost of ownership was not ranked as highly. And we found that this was mostly due to the competitive bid process where they have to purchase vehicles with the lowest purchase price. When we asked about total cost of ownership, some fleet managers reported that they did use it, but it was not for initial purchase considerations, and it was more used for deciding when to retire old vehicles or whether to repurchase the same vehicles again in the future. We then looked at fleet electrification questions, and we found that all but one of the 23 fleets that we interviewed had at least one plug-in vehicle in their fleet, and they reported having overall positive experiences with these vehicles. All but one fleet had a conventional hybrid electric vehicle, and 6 fleets had hydrogen vehicles. So exploring these decisions a little bit more deeply, we asked the fleet managers about their top reasons for purchasing an electric vehicle, and we found that electrification is largely driven by internal sustainability goals, the availability of grants and incentives, as well as just showing that the organization is a green leader in general. So generally, these sustainability goals came from within the organization itself, as opposed to like an outside source, such as the state. And some of these goals were more broad, such as those for purchasing green vehicles where possible, and others were more specific, such as purchasing 20% alternative fuel vehicles each year. So the second most commonly mentioned motivation for electrification is the availability of incentive and grant programs for the vehicles. And while some fleets mentioned that all of their electric vehicles had been purchased using these programs, some other fleets showed a general lack of awareness for their availability. These fleets mentioned that they were only aware of 1 or 2 programs that they were eligible for, and they didn't really know if these incentives could be combined with other incentives. Some fleets actually had dedicated staff people whose entire job it was to look for these incentive programs and apply for them. And unsurprisingly, these fleets were the ones who reported using the highest number of incentive programs. So nearly all of the fleets did use some sort of incentive, and the most commonly used incentive was the California State Rebate, which offers up to $2,000 for a full battery electric vehicle and $4,500 for a hydrogen vehicle. And fleet managers reported that after applying these incentives, the purchase price of the plug-in vehicles was actually about the same or less than a comparative gasoline vehicle. And overall, we found that roughly 14% or 3 fleets did not use any incentives. And they mostly said that this was because they were just too busy to look for them or did not know of any that were available. So we then followed this up with a discussion about the barriers that fleets had faced in electrifying and the reasons that they were unable to electrify more vehicles. The fleet managers mentioned 7 main barriers to electrification, with some fleets mentioning additional barriers that are more specific to the organization. And we put these in the other category. So access to charging infrastructure was seen as the most common barrier. And here, fleet managers said that the high cost and time required to install the infrastructure made it difficult to purchase these vehicles. And one of the main reasons for this is that the majority of fleets have a fixed annual budget. So this doesn't really account for the costs of installing infrastructure. Also, some organizations are structured so that the fleet manager is the one who makes the decision to purchase the electric vehicles, and then a separate department is in charge of procuring the infrastructure. So the various departments need to coordinate in order to have it installed. So fleet managers also mentioned encountering issues with employee buy-in and encouraging them to use the vehicles once they have been purchased and placed in the fleet. And they generally reported that after trying out the vehicles a few times, the employees got more used to using them and understanding their range. So notably, I put a picture of a Tesla police car on this slide because it's just a good way to get employees informed and excited about these vehicles, because it can help people understand that these electric vehicles aren't that different and can actually be more fun to drive. So just doing these more interactive and getting people excited can be really important. So in addition to the barriers that were directly mentioned by the fleets, there are a few topics that were discussed elsewhere in the interviews that sort of emerged as potential barriers to electrification. One of these is the need to purchase vehicles with the lowest upfront costs. And this can often exclude electric vehicles from purchase consideration. Additionally, we found that in some organizations, the fleet is responsible for paying the upfront costs of the vehicles, while the departments pay for the fuel costs. And in these cases, the central fleet really has no financial incentive to purchase the electric vehicles because they don't see the associated fuel costs. And so the combination of all these issues can make it difficult for fleets to use total cost of ownership in their vehicle purchase considerations. So then, looking at used vehicles, we found that some fleets indicated that they would be hesitant to purchase used electric vehicles, and we found that this was generally due to the lack of warranty and unknown maintenance needs of used vehicles. And their concerns included that by the time they purchase these vehicles, they are outdated and the technology and range are advancing so quickly that they want their employees to have like the best possible experience with these vehicles. So if they purchase used vehicles, they may not be getting the best experience. They also mentioned that these vehicles have a low residual value, so they can't really sell them for very much at the end of their use. And they said that they would need to go through a difficult exemption process to acquire these vehicles because they can't competitively bid them again. So a few fleets did indicate that they had purchased used vehicles in the past and that they'd be willing to again in the future, but these were generally for very specific purposes, such as undercover police work and access to HOV lanes. 27% of fleets indicated that they would consider purchasing a used EV under certain conditions. And they said that they may be willing to purchase them if they receive a significant discount on their purchase price, if the vehicles were guaranteed to be in a good condition, and if there were sufficient warranties available. So overall, we found that electrification is largely driven by fleets' internal sustainability goals, and that many fleets are trying to integrate them in wherever is feasible. One of the main barriers to this electrification process is that many fleets don't have access to dedicated charging infrastructure, and they found it very costly and time-consuming to install this infrastructure. While the majority of fleets talked about the importance of grant and incentive programs, they were often unaware of many of the programs that they were eligible for. And finally, we found that the perceived complications associated with procuring used vehicles are currently too high to allow for a high penetration of these vehicles into fleets. So while most vehicles have begun to electrify for use in various applications, there's still a lot of work that needs to be done. So we have a few recommendations for helping fleets to electrify. And the first is that there are many policies that can help encourage fleets to electrify, such as creating electric vehicle first policies, which can help circumvent the lowest bid purchase requirements. Also, increasing the ease of access and publicity of grants and rebates can help lower the upfront costs of these vehicles. Utilities can also play a role in providing charging infrastructure and incentives for fleets, so outreach to them can be really beneficial. And I again wanted to point out the picture that I have on this slide, which is actually a all-electric Chevy Bolt that they had sitting in the lobby after getting off a ride at Disney World. And they actually had it set up so that people could take a picture with it, and they had someone standing there to answer questions about it. And I just wanted to point out this because education efforts that are sort of non-conventional like this can help people be more aware of these vehicles, even if they aren't looking for more information about a vehicle like this. And fleets can sort of use non-conventional techniques such as this to help increase employee buy-in. So then for used vehicles, very similar to the new vehicles, the education efforts are really key. And one way to do this is by informing dealers about the hesitations that fleets have with used vehicles, which they can help alleviate by providing information, such as the longevity and reliability of the vehicles and batteries, and how to get charging infrastructure. Also, extending the warranties on these vehicles can be critical to help account for the risks of purchasing vehicles with unknown histories. And one potential way to do this could be through charging a low fixed monthly cost that is then used to cover the cost of repairs when they're needed. So in the end, we found that converting fleets to used electric vehicles can be pretty challenging, but it's not impossible. And we found that purchasing policies of many fleets don't currently allow for this, but it is possible to find exceptions to this. We found that the current lack of warranties on used vehicles is concerning to fleets, but extending manufacturers' warranties to these vehicles may help lessen these concerns. So while many fleets can be sort of averse to change, they may be open to new technologies once they've been more proven. And thank you. And yeah, any questions?
Yeah, Claire, you do have a question. I thought I heard your cat in the background. It sounds like my cat doesn't like to be left out. So you have a question from your colleague, Ryan Barr. So Ryan, I'm gonna unmute you. All right, Ryan, you should be unmuted.
Hope you can hear me.
Yes.
So I'm just wondering what incentive programs like grants, rebates exist for fleet operators to electrify their vehicles.
Yeah, so the big one that we found is the California state rebate, which is the CVRP, which is the same one that is available to private consumers. And fleets can use up to 30 of those rebates a year for their vehicles. And then there's a lot of really like little specific ones that are available through like the air districts and local utilities. Usually the utilities are focused more on providing like charging infrastructure incentives. And then there is the federal government rebate that some fleets can apply for. But because public fleets don't have any federal tax liability, they can't take advantage of that unless they lease their vehicles and the dealership applies for it. So it is really specific and complicated, the whole grant and incentive program for fleets. But yeah, there are a lot out there.
Thanks. And a quick follow-up question on that, if that's okay. I'm wondering if you're aware of any good data sources on which fleets have procured electric vehicles and ideally when and what kinds, that kind of thing.
I don't know of any that cover like multiple fleets like that with all that specific information, but like individual fleets tend to have that sort of information up on their websites. And there's like fleet organizations like Public Fleet Supervisors Association and National Association of Fleet something professionals maybe, that are sort of organizations where fleet managers sort of go and talk about possibilities of electrification and greening and all sorts of other fleet issues. So looking through those could give you a good idea of maybe who electrifies. But I don't know of any specific that have all the fleets listed with their numbers of electrification.
Great, thank you.
Great. It looks like Austin may have put something in the chat here about Clean Cities program, keep some fleet data. So that might be another place to look. Any other questions? Please feel free to let us know and we'll get you some time with our presenters here. Also, if you have questions from Dave that you thought of during the last presentation, feel free to put your name in there and we'll get those to Dave as well. All right, well, I provided the emails for both presenters and Claire has hers up there on the last presentation slide as well. So feel free to follow up if you have additional questions. Thank you so much for joining us. We hope you can join us again next week where we'll have our last Energy Bites for the quarter. And have a wonderful long weekend and we look forward to connecting with you again. Take care, everybody, and thanks so much to our presenters, Claire and Dave. You did a great job.